This experiment studies the rate of a chemical reaction. This is completed by monitoring the concentration of one reactant as a function of time. Since this reactant has a visible color, and since the intensity of the color is proportional to the reactant's concentration, a UV-Vis spectrophotometer can be used to monitor the change in reactant concentration over time. Several reaction mixtures which differ in reactant concentration are run at the same time, and graphs are plotted of these mixtures which show how the rate is dependent on reactant concentration. Eventually, the rate law is determined, which specifies the order with respect to each of the reactants as well as the value of the rate constant. A total of 4 reaction mixtures are prepared, with all 4 reactions started at the same time. Your lab measurements will involve recording UV-Vis absorbance data of the cobalt complex in the reaction, which is one of the 2 reactants in this experiment. The order for each reactant is either 0th, 1st, or 2nd order, and after determining the observed rate constant KOBS, the rate constant K can be determined. The orders and value for K are determined graphically, so it's important to collect accurate data. After determining the rate constant and order for each reactant, the rate law for this reaction can be defined. In this experiment, azidopentamine cobalt-3 reacts with hexaquyl iron 2. This redox reaction involves a 1-electron transfer from the iron complex to the cobalt complex, resulting in the oxidation of iron and reduction of cobalt. The ammonia and azide ligands are released during the reaction, with the hexaquyl cobalt-2 and hexaquyl iron 3 complexes formed as products. The rate-determining step involves the azide ion, or N3-, bonding to both cobalt and iron, acting as a bridge to temporarily form this transition state intermediate. The formation of this bridged intermediate facilitates the transfer of the single electron from the iron to the cobalt and dictates how fast products are formed from reactants. After the electron is transferred from iron to cobalt, the bridged intermediate falls apart, forming the products of the reaction. The reaction conditions are manipulated such that the azidopentamine cobalt-3 is the limiting reagent. When this cobalt complex has completely reacted, no more products can be formed. Another experimental design feature involves making the concentration of hexaquyl iron 2 reactant much greater than the concentration of the cobalt reactant. This means that the concentration of the iron reactant is effectively constant during the course of the reaction. This design allows the determination of the rate constant K to be graphically determined. The change in concentration of the cobalt reactant is monitored at 517 nanometer, which is its wavelength of maximum absorbance. When the electron transfer occurs in the bridged intermediate, the ligands in this complex are freed, and the absorbance at 517 nanometer decreases. This decrease in absorbance is used to monitor the change in concentration of the cobalt reactant and ultimately the rate at which the reaction progresses. The change in concentration can be plotted on an XY graph. As stated previously, the hexaquyl iron 2 reactant is much more concentrated than the cobalt reactant, so its concentration remains constant during the reaction. As the cobalt reactant concentration decreases during the reaction, the hexaquyl iron 3 product increases. The rate law expression can be simplified. Since both the rate constant K and the hexaquyl iron 2 concentration are constants, they can be combined into the observed rate constant KOBS. Then the rate is simply equal to the product of the observed rate constant and the concentration of the azidopentamine cobalt-3 raised to the power of P. Listed below are rate constants for several reactions involving a variety of cobalt complexes reacting with iron 2. The cobalt has a +3 oxidation number in all of these complexes, and the ligand environment greatly affects the rate of the reaction. The fastest reaction has the largest rate constant K. For this series of complexes, there is over a 1,000-fold difference in rate. Here is another series of cobalt complexes, where the rate is affected not only by the difference in one monodentate ligand, a halogen, but also the ionic strength mu, which is a measure of the total charge contributed by all ions in solution. As ionic strength increases from 0.34 to 1.7 in this series, the rate of each reaction also increases. Ionic strength can be increased by adding a salt or acid to the reaction solution, and although the acid or salt may not be required to balance a chemical equation, the resulting increase in ionic strength can change the rate constant or velocity of the reaction. To measure the velocity of a reaction, the concentration of a reactant or product must be monitored during the reaction. Beer's law states that for a substance that imparts color to a solution, the concentration of that substance is directly proportional to the absorbance of the color of the dissolved substance. For this experiment's reaction, the azidopentamine cobalt-3 complex absorbs light at 517 nanometer. The hexaquyl iron 2 reactant and the products of this reaction do not absorb light at this wavelength. Therefore, by measuring any change in absorbance at 517 nanometer during the reaction, we are actually measuring the change in concentration of the azidopentamine cobalt-3 complex. Since this cobalt complex is a reactant, we should expect the absorbance to decrease during the course of the reaction, since its concentration decreases as the reaction progresses. The instrument used to measure absorbance of solutions is an ultraviolet visible spectrophotometer. This particular model used in lab allows multiple reaction samples to be measured. In this experiment, you will prepare 4 reaction mixtures and will record the change in absorbance, or concentration, of the cobalt reactant in each of these mixtures. This instrument, the Genesis 5 spectrophotometer, must be programmed to collect absorbance data at 517 nanometer for 4 reaction mixtures at a set time interval. It is relatively easy to use, and 10 to 12 minutes is normally adequate to collect a sufficient amount of absorbance data for all reaction mixtures. Here is a set of representative data collected at 30-second intervals for just under 10 minutes. Note that the absorbance decreases with time, which is quite typical of the concentration of a reactant as it decreases while the reaction progresses. There are several pitfalls to avoid in this experiment. Digital pipetters are used to dispense accurate solution volumes in this experiment. A careless dispensing can ruin the data collected by the spectrophotometer. Your 10 ml graduated cylinder should not be used to measure any solution volume. The digital pipetters are more accurate. The 4 members in your group must mix their individual reaction solutions at the same time. The cuvettes used to hold the reaction mixtures have 2 sets of opposite sides, a frosty pair of sides and a transparent pair of sides. The transparent sides must be in the path of the Genesis 5's light beam. The absorbance of each reaction mixture after collecting data and then heating it to completion must be recorded. The final reading is called the absorbance at time equal infinity and will be the lowest recorded absorbance.